The real problem is that most tone arms do not move like this. And I think the reason we have to go into this is because often you'll get manufacturers who claim this is a no compromise arm. It's got zero tracking error. There's trade-offs with that, which are never mentioned.
You're never making things more linear. You're just repositioning where that perfectly tangent point is. Every geometry is a compromise. Many audiophiles are desperate to get rid of tracking error on their turntables. And this has resulted in a lot of tonearm designs to solve the issue. So from linear trackers to tangential arms, even underslung zero offset tonearms or things like pivoting headshells. And you could also think about the different cartridge alignment geometries that are used to reduce tracking error and distortion. In this video, we're asking, how much does tracking error actually matter? And what are the problems involved when we try to reduce it? Hello, I'm David Baker of Origin Live. This is my dad and our company's founder, Mark Baker. Mark's been designing tonearms for over 30 years, so you know a thing or two. Let's get right to it. So what is tracking error?
Tracking error is the lateral angular deviation from the stylus being absolutely in a dead straight line with the record groove. But I think I probably need to explain what that means because it's a bit much to digest. So we need to start really with how the record is cut. And if we imagine a record cutting lathe, you've got your record here, and the record cutting lathe will be moving in a line across the disc like this. And as it goes, it kind of vibrates both horizontally and vertically to make the groove in the lacquer disc, isn't it?
Yeah.
Because they then make a pressing out of that, and then you start pressing the records. So the real problem is that most tone arms do not move like this. Obviously the linear trackers do, and the tangential trackers move similar. But most tone arms, and I'd say 95% of the market probably, move in an arc like this, which means that they're not at right angles to the groove like they should be. They're at a slight angle.
Okay, and why is that an issue?
Well, let's just draw another diagram. So these angular tracking errors they're quite small, but they do have an effect on the record. And so I'm going to just draw a very exaggerated diagram now to kind of illustrate why this is the case. If we imagine our groove and it's full of bumps, okay. I don't like doing this diagram. It's not an easy one to understand. So you're going to have to use your imagination. But this series of bumps is moving at 30, whatever it is. The speed, of course, varies depending on where you are on the record. But they are moving in that direction. And you've got your stylus, which is moving between. You've got that's your needle here, and it's sat in the groove, moving backwards and forwards. Now, if it's in perfect alignment with the groove, like I've drawn it, it's going to move like so. It's not, that's obviously as the groove passes. However, and I'm going to exaggerate this because it's the only way. If you exaggerate things, it's always much more easy to understand.
So just before we go on, so this is currently at a right angle.
Yeah.
So linear tracker, tangential, pivoting headshell, for most of the record, it will be at this angle.
Yeah.
And then with our pivoted arm, there'll be 2 points on the record where it's in a right angle, right? The 2 nodes, but then there are other areas where actually it's at an angle.
Yeah.
Is that right? Okay.
Yes, that's right.
So what does it look like when it's at an angle?
Okay. So I'm going to exaggerate a stylus at an angle. Okay. So if the stylus is like that, instead of moving like this in the groove, it's going to move like that in the groove. Okay. So your contact point with the wall will be different to where, if it's at right angles to the groove.
Okay.
And that has an audible effect because it introduces phase errors, which are important. Okay, so the first thing we've got to try and think about is how we can minimize your tracking error. And I think it's a guy called Wilson who first came up with this. But if we imagine that's the center of the record, and the record is like so. As the stylus kind of traverses the record, it does so in an arc, as we've already discussed. What Wilson discovered is that if you create an overhang from the arc, if our pivot center is about here, then what you can get is that when it does this arc, it will actually be tangential, perfectly tangential at 2 points in the record. And most of the alignment gauges, depending on what's the alignment geometries called?
Well, you've got Beowulf, Lofgren, they have some different variations of those, and then Stevenson will be an Exxon use.
So the various alignment geometries tend to move where these null points are. In other words, some will have the null points here and here, which means that your inner tracks will play better. And it's really just a question of compromise. But in principle, this is how you can minimize your tracking error.
So you found by taking the cartridge stylus beyond the center of your record, you can achieve 2 points of tangency. Okay, how interesting. Okay.
Yes, and then there's the configuration that you mentioned a bit earlier, which is where you've got what you call an underhung. Underslung. And that only contacts...
These are often zero offset.
Yeah, so the geometry on an underslung is not as good, and we'll get on to why people do this, but...
Controversial.
Yeah, we won't get to the geometry there, but that is only going to be at perfect right angle to the groove at 1 point. So it's not as good for geometry, but they generate less side force. But we'll go into that later on. So the first thing to understand is this is the way that we have different geometries, or alignments, I should say, for your tracking, to minimize tracking error.
So that's why we have overhang, but also on most pivoted arms, we have an offset. Why is that?
There is one little wrinkle we need to explain here, and that is that even though it arcs like that, you actually have to get the stylus to actually be at right angles to the groove, you actually have to put an offset onto the angle of the arm itself. Now, it's beyond the subject of this particular talk to be able to go into all the geometry regarding this, but that's what you call the offset angle. A couple of little takeaways is that the longer your tone arm is, the less your overhang, the less your offset angle, the less your anti-skating force is.
Oh, so that's because the wider arc requires less offset.
That's right, yeah, and less overhang. All right. So that's a very brief introduction to the geometry of how we kind of reduce the offset errors. But these have some quite interesting side effects which have to be mentioned. And I mean, it's almost like, why does this matter in a talk about geometry? But there's a lot of factors that interplay with this, with tone arms, and it can get very confusing. So we'll try and keep it simple. We're certainly not going to go into the maths.
Well, it's always with tone arms, you try to solve one issue and more arise.
Exactly.
Everything is interwoven, as you say.
And I think the reason we have to go into this is because often you'll get manufacturers who claim this is a no compromise arm. It's got zero tracking error. There's trade-offs with that, which are never mentioned. And with all of this, it is a constant balancing exercise between various factors which conflict with each other.
Yeah, absolutely.
And we'll get on. You'll see why later on in the talk why we go there. The most important thing to talk about with anything that has a pivoting action is what we call skating force. And this is quite counterintuitive. I mean, most people, when they see a stylus tracking through a record, they expect the force to be like centrifugal force, like kids on a playground roundabout, that's kind of wanting to throw them off.
Okay.
Yeah, it's wanting to throw them off like that. The exact opposite is true with a tone arm. And it's the only reason the only way you can understand that is by understanding offsets. So what's actually happening here is that I haven't drawn this terribly well, but this arc should kind of go through at perfect right angle to the head shell. And because of the friction on the record, you've got a force generated like that. But that force is not in line with the actual arm tube. Okay,
Right.
so it becomes like a lever, and this is your levering distance. So the tendency is always to pull the arm in that direction. So it's actually
Right.
being levered inwards.
Right.
And that is counteracted. So that's skating force, and that's the skating force is to pull it in. So what tonearm manufacturers do to get over that problem is they put a side bias on the, well, they can put it almost anywhere on the tube actually, but anywhere on the tube or turret so that it will force that in the opposite direction. So it will want to pull it like so.
Right.
All right, so that's being pulled that way, but on this end of the arm, you're pulling it this way.
So to summarize, the offset at our head shell is actually, the angle of that is dragging the tonearm assembly inwards. And we need to apply a countermeasure to that, which is side bias. Because when we don't have any side bias applied, generally, well, I hear this manifesting as the image will actually be slightly off center. So the way I usually dial in side bias is find a track with a central singer, adjust side bias until that singer is bang in the center.
Yeah.
But when I'm not, they're quite clearly over to one side because of the effect of side force.
Yeah. No, I'd agree with that. And also I would say that the way I tend to listen is the separation between the instruments tends to improve
Absolutely.
a lot when you get the side bias right.
The focus for clarity.
Yeah.
Absolutely.
Yeah. Well, the cure is side bias. There are a number of kind of problems with side bias. I mean, in a perfect world, all right, if everything was wonderful, in a perfect world, you can apply your side bias force, and the side force of the stylus in the groove will be zero because, you know, it's being guided down the groove perfectly. In practice, never happens. And this is why people get a bit worked up about side bias, like I do, because I was put onto this years ago by a friend of mine. And there's kind of, the perfect world doesn't exist in the record player, because what's happening is, first of all, when you're off your two perfect points where this thing is in alignment, you've got a geometry error, and you'll get a different side bias force simply by the fact that the stylus is at a slightly different angle. But an even bigger one than that is the fact that the drag of the record varies all the time. And that's not just talking about from the inner grooves to the outer grooves, from the outer grooves to the inner grooves.
Although it is worse on the inner grooves, isn't it? Yeah.
Because your velocity of the track out here is a lot higher than the velocity of the track here. But you've also got things what you call high intermodulation tracks, where, I mean, like when the crescendo of an orchestra, for instance, there is a lot more drag on that track, on that groove, than there is when it's just playing a gentle solo singer or a violin or something in the background. So the drag
is that because
actually,
there's so much more. Is that because it's a more dynamic passage, or because it's a more busy passage?
it's both.
Right.
Yeah, it's both. But the net effect of that increase in friction, because that's what's happening, is that your skating force goes right up, and your side bias is left standing where it's been set. Okay, so you are going to have, it's an imperfect solution because you will have sidewall force. And as we've explained, sidewall force has repercussions, like your imaging will tend to break up a bit and so on. So,
and separation and
Yeah.
and
so that's why sidewall force is important. A lot of people don't kind of recognize why it's important, but and why side bias is not a cure-all. Okay, it's the best solution we can come up with, because there really isn't anything else apart from going to linear trackers and tangential trackers and pivoting head shells and the like. So just to clarify one thing, because people may think, oh, because the velocity is much higher here, that the side force must vary massively across the record. It actually doesn't, because when you get to the inner tracks, there is a lot more modulation in there. In other words, the track has a lot more bumps. So the friction level on the inside goes up because of that,
and does the
even
track
though the
have
speed
more,
is down.
The track have more bumps because it's more compressed at that point?
Yes.
Right. Okay.
Yes, that's right, yeah.
Okay.
So the producers of records have calculated all this out, greater minds than mine, I think. And they figured it out so that they try and keep the skating force even across the record.
Mm-hmm. Is it in practice even, or does it get worse at the end?
It really varies on the record.
Oh, okay.
Because, as I say, if you've got a heavily modulated track, because of the type of music on the inner tracks, it'll be different. So it's almost, this is the problem, is that there is a lot of variation.
Hi, I'm quickly interrupting this video just to ask that if you're finding it worthwhile, please could you hit the like button, subscribe to the channel, and also press the bell notification. It really helps us to carry on making these videos. And yeah, what we want to do is carry on having open conversations about vinyl replay, and also giving you insights into how we've been making turntables and tonearms in-house in the UK since 1986. Well, not me personally, because I'm 31, and that's... Anyway, you get the idea. So thanks, and back to the video.
Yeah, okay, so a company called ViV, no, that's the actual name of the arm, I think, the ViV. Okay, so a while ago, there was a new arm appeared on the scene, and the designer had a very interesting take on this. And basically what he said is, I'm not going to worry too much about the error angles.
Okay, like the tracking error, the LTE, the nodes, all of that kind of stuff.
Yeah, the lateral tracking angle error and so on. I'm not going to worry so much about that. I'm going to worry about the side force generated. So what he did was he came up with a design where the arm is underslung and it only contacts the record at a right angle at one point.
So underslung means it doesn't have overhang.
Exactly, yeah, yeah. So
and generally with that there, so I think this is 7 inches long.
Yeah, so if you do an arc, it doesn't go over the record spindle, it goes in front of it. And this arm had various other features, like you could just stick it straight down on a record player as just a base.
Yeah.
It floats in ferrofluid, so it's very low friction. Maybe low friction, but vibration feeds through ferrofluid like crazy. Anyway, this arm has a much lower side force on it than a normal conventional arm which has a large offset angle. This has no offset angle whatsoever, and it just makes contact with the arc across the record at a single point. And the offset error, the angular error is significantly higher on other parts of the record. Like out here, there's no competition between the error you get on that, the geometrical error, and this type. So the question is, which is better? And this arm had a very good following at one point.
I think it still does, to be honest. Yeah.
Right, okay, yeah, because they are both important.
Okay, so that's really interesting.
So what we're going to get onto now is some of the other ways around this problem, and we're going to move into the arms where there is no tracking error whatsoever. And there are various ways that people have used to get over these problems, and we'll go through them.
Okay, so arms that have no tracking error, where do we start? What designs?
Well, I think the simplest idea is a pivoting headshell. So there's a very clever headshell on the market, and apparently you can just screw this onto any
removable headshell.
The removable headshells which are used on Technics and the like.
Yeah, so this is the NASOTEC headshell you brought to my attention.
Ingenious idea. It's one that has occurred to me in the past as well, but it's interesting to see someone actually put it into production. So with this, what they do is they put a little pivot in here, and the headshell, if you can just draw it straight. You've got your stylus out here, which is sort of dragging on the groove. But because the groove has drag on it, the whole head shell can basically swing about this pivot backwards and forwards. So it perfectly aligns with the groove at any point in time. Now, if in practice, if you did do such a design, and they do, then this would just flop around like crazy when you were trying to cue the arm up. So to kind of save the thing going mad, what they do is they put a little couple of springs, very lightly loaded springs on the side here, to just kind of hold the thing in check. So, you know, it doesn't go mad. But those springs are very lightly tensioned, and the thing does align with the groove very nicely.
Is that because, why does it stay in line? Is that because the groove is kind of keeping it, the groove is running it in alignment?
Yeah,
okay,
that's right.
amazing.
It just drags it into alignment.
Wow.
And it's always at a perfect right angle to the groove,
Okay.
which is an ingenious idea. The only reason that I didn't go down this road was because the sacrifice of the rigidity of the arm.
Yeah, yeah. Okay. When you drew those springs, I was like, oh.
Well, they will vibrate as well.
Yeah.
But it does sacrifice the rigidity of the arm. So instead of the inertia of the whole arm holding that cartridge steady, you've basically, it's like it's free to just bob around basically. So the inertia is severe, is taken down. Okay, so that's one solution. Okay, so the next kind of logical progression from the pivoting head shell, which has not a lot of rigidity, is to do what the Thales Tonearm did. And this is quite a high-end arm with a very good reputation. And what they do, and I can't draw this because it's too complicated, but in principle, what they do is they have two arms, tubes. Okay, and there's a cam device of some description in here, I imagine, which means that as the head shell is moved across the record, these arms control the angle of the head shell.
Oh, so these are two.
These are two
arms.
tubes. Yeah,
okay.
those are two tubes, and basically they change position slightly, so there's a kind of seesaw motion like this because they're controlled by a cam device here. And I've drawn these things myself, and they're quite complicated, so I'm not going to get into the geometry of it. It took me about 3 days to figure out how a tangential arm geometry worked perfectly. So anyway, what the net result is you've got an arm which does track in an arc, but the head shell is still maintained at a perfect right angle to the groove, and it's fairly rigid. Okay, so that's one way of solving the angle problem, tracking angle problem.
Okay, pivoting head shells. What's next?
So we've discussed the Thales arm, but if you want to get away from having joints in the head shell area and the very slight loss of rigidity that those joints will introduce, then the way to go is what you call a tangential tracker.
Okay.
And this is where you have your head shell conventionally attached to the tonearm. But what happens is that the pivot of the tonearm actually physically, well, the pivot which controls the vertical movement, actually physically moves in relation to the record.
So the base of the arm itself is moving.
Yeah, what you call there's going to be your fixed base, and then you're going to have your moving base, and it's the moving base which is moving. And it does, the way it does that is it controls the arc by using a couple of levers, basically. Very difficult to draw, so I'm not going to. But in principle, I mean, there's examples of this. There's 3 arms which do this method at the moment that I'm aware of. You've got the
Reed,
the Thales, if that's the way you say it.
I thought it was Tela.
Tela.
I don't know.
Okay.
Hopefully somebody knows.
Yeah, and then the Schroeder have an arm as well.
Right.
That uses their tangential tracker. They tend to be very high end, because to make these pivoting motions, these pivots rigid, and so that they don't create vibration and all the other sort of anomalies that creep in when you have quite a complexity, add complexity to the arm. It means it has to be high end, and it's a lot of design work goes into one of these arms.
Cost of manufacture, cost of development.
Yeah.
Yeah. And the interesting thing about these is that they don't actually move in a perfectly straight line, do they?
No.
So they're moving at a right angle to the groove.
Yeah.
But it's kind of constantly moving slightly forwards.
That's it. Yeah.
Right, is that correct?
Yeah.
Okay.
Yeah.
Is that similar with the pivoting headshell, or?
No, it isn't. The
No.
pivoting headshell is just maintains a perfect arc across the record. It's just that the headshell moves.
Is it,
But
it
only it's
maintains
the whole...
a straight line, or it kind of still arcs but stays tangent?
Yes, that's right. Yeah.
Okay, okay.
Yeah. Okay, so what we're going to talk about now is linear tracking arms.
Okay.
And in theory, a linear tracking arm is the perfect solution because basically you've got your record and the linear tracking arm is mounted on a rail of some description. So the arm tube is basically a perfect right angle to the groove at all times because it follows the cutting lathes motion of moving straight across. So this is very attractive. And if you want to avoid a whole host of other problems, this is the way to go. It would appear.
Yeah, okay.
Now, I quite favoured parallel trackers for a while, and I actually got to the stage of designing one start to finish, and I had it all thought out. And a friend of mine was experimenting with them as well. He was using air bearings. I was going to use rollers because I thought that was, people don't want a noisy pump in the next, sorry, they're very quiet pumps, but you still have to use an air pump to have this going. So that's got to be maintained. They can be a bit noisy. Some people have to put them in the next door room.
Okay.
And there's quite a workup with linear tracking arms. Apart from just the sheer bulk of the thing, they're sometimes quite problematic to mount on a small deck because there's just no space for the mounting. But ignoring all those problems, what are the issues with a linear tracking arm? And the first one for me is, and this is very, very controversial and arguable, and I respect anybody who has a contrary opinion. There are some very good linear tracking arms on the market. My kind of concern, I suppose, is that you've got quite a high inertia. So you've got with a pivoting arm, there's very low sidewall force. In theory, because you've got side bias attachment, in theory, you've got zero sidewall force. But in practice, as we've discussed, that is not realistic because you do have variable skating all the way through the record. So there's a strong argument to say that, that's actually not, that this could have less sidewall force. But the sidewall force comes because of the sheer inertia of the thing. It's got 3 times the inertia. Even if you've got, say, a 60-gram parallel tracker, you've got to get this whole assembly down. Because the whole thing moves, the inertia is the whole arm, all right? Very difficult to get the weight down. So people use short tubes but then you get, problem with short tubes, all right, very quickly is quite obvious. You've got a lot more vertical tracking error because if the arm only pivots here, you've got more vertical tracking error.
Right.
Okay, so going to a short arm, even though it reduces rigidity, is not a good idea for vertical tracking error. If you can imagine a very long pole pivoting back here, the tracking error angle is much, much less.
Okay. So it's the way it actually affects the angle of the stylus.
Yes,
where it's
exactly.
so short.
Exactly.
Okay.
Yeah. So that's the first problem. The other problem is just getting the weight down. You have to make enormous sacrifices to get the weight down, and that has other issues because without kind of going into it, you do want weight in the right place on the tonearm.
Yeah. We wouldn't. There are some people who say you don't want any mass, but actually you have to have mass in some places in order to absorb reflections, handle some of the inertia, dampen some of the joints, all of that kind of stuff.
Yeah.
Mass is actually quite useful.
Yeah.
Okay. So whereas a pivot alleviates some of that mass, all of the mass is here, all of the mass of the tonearm is on a...
Yeah.
Okay. And
So-
why is that an issue, I guess?
Why is weight an issue? Well, this is where it gets a little bit arguable, really. But if you have an off-center record, say, you've got to move. This thing has to. The whole groove is constantly moving in and out slightly, only by maybe about 0.2 of a millimeter.
I think it's 0.2 mil is around the max. Yeah.
Yeah, I've seen offset center records which are a lot higher than that. I mean, you know, it's they have a special tool, don't they, just to center the record.
Oh, the DS. It's good.
The
Yeah,
DS,
it's good. It works. Yeah.
But that proves that this 0.2 standard is absolute nonsense. I mean, you know, it might be the standard, but very few, it's not always stuck to. So you've got to move the whole assembly backwards and forwards with 3 times the side force because of the inertial side force, because you've got to move that mass. And the other thing you've got to do is the whole thing actually has to move from point A to point B. And in moving from here to there, it's going to have side force, because the only thing to physically moving this is the groove. So it has to do that by pushing, and that is a side force. That's a sidewall force to move this physically from there from A to B.
And is that a different type of force to the inertia of an eccentric groove?
It is, yes. Yes, you're just simply moving the whole, it's only moving in one direction. But if you imagine taking this argument to the extreme, right, if that was a ton which you had to move along and it did move perfectly through the groove, you would definitely get wear. Now the argument is that wear significant? Is that side force enough to cause the errors that we've been talking about in terms of side forces tend to introduce problems sonically. I would suggest it's there, but it's probably not that great.
Okay.
So I think that just about covers the linear trackers.
Okay, so I think finishing off, maybe the last thing we should discuss is cartridge alignment geometries, which is a bit of a mouthful.
Well, 95% of the market is using alignment geometries, aren't they? So
most arms
it's
are
an
pivoted.
important area.
Most arms are pivoted.
Yeah.
Most arms are going to have are arcing. Most arms are going to have a certain type of geometry. Now this is really going to be so far from comprehensive, and this is very off-center.
You've got a degree in fine art. Is that a circle?
Yeah, you know, Picasso style. Now, I guess the thing to say here is that we cannot make a pivoted arm more linear, right? Because there's always going to be, it's always going to arc. With our different alignment geometries, what we do have control over is where we put those areas of tangency, where we put those null points where there's zero tracking error. So if we think about that as our arc, we will always recommend the Beowulf alignment, which I think is Lofgren A or Lofgren B, I can't remember.
It's Lofgren A.
And this places the null points around here, and essentially this gives you the least tracking error on average across the entire record surface. So it's not too skewed in one direction. Now the interesting thing about something like the Stevenson is, this is a very bad illustration, but imagine our inner groove is here. On the Stevenson, the first null point is a little bit further over, and the last null point is bang on the end of the inner groove. So they've got perfect tangency at the very end of the record. And this is a very interesting one because for most of the beginning, you're going to get more tracking error. Although it's potentially arguable that the tracking error for this entire portion of the record, results in less distortion than the very end. I'm not sure how much I agree with that, but anyway, that's kind of one of the thoughts. But you'll have more tracking error here and less tracking error here. This is often kind of recommended for classical music lovers, that kind of thing, where you've got a great finale and crescendo. Maybe you want the end to be the most perfect sounding. It's curious that both Technics and Riga opt for Stevenson. Not entirely sure why, because for a mass market turntable, you'd think that most people aren't listening to classical. There's no hate on classical. I'm a big classical lover, but I find that very curious. Anyway, we personally go for Beowulf Lofgren B is slightly different, and I think maybe it doesn't have the lowest overall average distortion, but it has the lowest overall peaks. But this is very uncomprehensive, but just to say that with all cartridge alignments, you're never making things more linear, you're just repositioning where that perfectly tangent point is. Every geometry is a compromise. You might kind of want to adapt it for what type of genre music you like, or also even to some degree what records you use. So for instance, a lot of the MoFi records try to cut, closer to the outer groove because there's less distortion. So you'd assume you wouldn't, if you're playing all audiophile records, you probably wouldn't want to be using Stevenson. You'd want to be using something that skews the null points towards the center of the record, and the outer edge of the record, because that's the area where your tracks are. But yes, there are swings and roundabouts. Another geometry I really want to explore is Unidin, that was mentioned to us by Roy Gregory. Haven't really had much opportunity to figure out that, but that's something I want to have a proper listen to.
Yeah, I think it all depends if your favourite track is on the outside or the inside of the record.
Yeah,
really.
Yeah,
because it's just whatever you end up with is a compromise, and
absolutely.
The inner tracks are much more difficult for the stylist to negotiate, and that's why people favour making like the Stevenson, that you bias it towards the inner tracks playing at more of a right angle.
Yeah, and annoyingly, I do have a few albums where my favourite track is on the inside.
Yeah.
But in all of these things, it's about enjoying the music still.
Yeah, exactly.
Anyway, right.
Exactly.
So that is our take on tracking error, and perhaps just as important as tracking error is side force. Thank you so much for watching. Please like, subscribe, ring the bell notification. That really helps us out. Let us know your thoughts. Are you a zero offset aficionado? Do you have a zero tracking error tonearm, or do you just live with it? And what kind of cartridge alignment geometry do you use? Thank you so much for watching, and until next time, enjoy the music.